hope you guys actually think it through. Okay. So the encapsulation concept, add the transport layer header, everything, add another header, right? Everything, right? Keep adding. Let's add the frame header. Then send it out. Here is see everything here. Next, remove those physical link layer header. Only have one network layer header, but the transport header still they will never touch the transport layer header. Make sense? They will check, make decision. Now they need to make the new frame link layer header, include the corresponding new information there. Got it? This is the remove process. This is one of the key concepts, the encapsulation concept, what actually happening there. It's really, really important. Okay? Everybody's fine, right? Talk about the encapsulation. If you translate your C into this, which is this slides, talking about the upper layer and the lower layer, how do they move the information from upper layer to the lower layer, add the corresponding information there, this header there. Okay, that's the encapsulation concept. Then, remember, for each layer, we might have a multiple protocols. We already clear with that, right? So for application layer, depends on different application, you have a different application layer header in the protocols. Then the transport layer, at least we know we have a TCP and UDP, right? For the internet network layer, at least we know we have IP version 4, version 6. We also have other companion protocols. You guys still remember last time when you try to check the routing information, you guys remember the SMP protocol, which is also a network layer protocol. They also have other protocols, the major protocols in here, okay? For the history, please watch those history by yourself, okay? I will quickly show the few history block. So like I mentioned, the internet, first start of the internet is based on the packet switching, right? Packet switching, major concept in packet switching start from a NASA project. Then it's getting bigger and bigger. Make sense? That's from the 1960 to 70. The early wide packet switching is one of the key concepts for the internet. Okay? See, with the first email and initially how many nodes are there. Initial internet is really small. Later on, more and more organizations join to the internet. Some of you have heard about the Aloha, right? The Hawaii, University of Hawaii, what is famous for. Then, those kind of concepts from the 70 to 80, the internet is getting bigger. Along this process, some of the technology might disappear. Makes sense? Along the time, all kinds of reasons. Okay? Like the Xerox Park still is a really important research center, right? Some of you heard like the Biolab research, also huge in those kind of history part. Those similar things from network part, Xerox Park is important there. And those kind of architecture, many of you may not heard it now. But it used to be really important because I used to work at the aviation industry. Those kind of network protocol at that time is important. Okay. Then later on, some of you may heard about the ATM, right? Then ATM also used to be important. Then later on, the Cisco's router went through. So ATM is not that important, but at the network core, maybe some of the ATM network still there. That's basically talk about the internet is the network of networks, and it's not also what it's heterogeneous, all kinds of network because those kind of past technology could still be there. Okay, that's to tell you along those years many things are happening, and then in the 1980 and the 80 and the 90. TCP/IP is start to get more important, and there are new protocols, and the network is getting important. I remember when I first accessed the internet, I guess it's late 80 something. is really popular. That's why my personal email, I'm still using the Yahoo. It's from history perspective. Also, I have Gmail, but my personal, I still like Yahoo. Because that time Yahoo is getting popular very fast. Okay. Then you look at those TCP/IP, SMTP for the email, then DNS, domain name service, and then FTP. FTP usually that time when we try to translate the files, we use the FTP, but not now, right? Because your email attachment, all kinds of new protocol is already coming up. TCP, congestion control. What is congestion control? Flow control. Those concepts actually along the history is really important. Okay, you guys still remember when we talk about the packet switching based internet, right? Well, the key things it can support more users compared to service switching, right? Then at the same time, nothing is like cannot be, all the pros, right? In some cases, they still have congestion issues, right? Like in the 290, when the class is over, we should have no problem. But sometimes, if something happens, it could be congested. Same thing because internet is packet switching based, the congestion could be an issue. So congestion control is really, really important concept. How to solve this congestion control? Make sense? That's basically they put some kind of important technology as in these slides. 1990 and 2000. Then you guys know the dot-com bubble, right? I don't know your guys' age, depends your guys' age. At that time, everything is getting a little bit crazy, and the internet is getting a little bit popular. See, the NSF also joined, multiple organizations joined, and the web is getting popular. That's why HTTP, HTML, all those things is getting really, really popular. Okay? That's basically 1990 to 2000. More users here. Question asked you, what's happening in the recent years? What's the new technology for the recent years? That's basically, please watch those history. But when you have new application, we're always looking for the new killer application. The killer application actually will change lots of things. Make sense? That's basically, think about along the years, what your phone changed, how many phones you have, each generation. Okay? Then at each generation, the phones, what application you are using. Then think about how you buy stuff. Think about how you get the information from. Okay? Okay, we used to, like each family, whole family sit on the couch at a certain time, we watch the news all the time, at the same time, right? The family kind of thing. Do that still happen? Sit together watching TV? Maybe last night, Super Bowl party, right? But typically, not that makes sense. So that's along the years, many things change. Think about all those kind of social networks. Then, if you want to make the social network work, what's the characteristic of the social network? Make sense? And then think about all the streaming part. Like many of you are using Netflix to watch things, right? All those new applications, the cloud, okay? That's basically check out the reason. I hope you watch it and think it. All those kind of, because of new application, what does it mean? Any kind of application, they need what? They need support from the network. Make sense? So in that case, there are two questions. What's the application's requirement for the network? Depends on different applications, right? So if our network architecture, network support or functionality cannot support that makes the application is not thriving yet, right? It's basically application and network, they need to support each other. We recently think about along the wireless part, maybe this is a network. We are not putting too much effort on the wireless network. Our department should have a specific class into the wireless network, but the wireless technology is really, really important. If the Wi-Fi technology is not here, if you're still using your phone, if the bandwidth is not working enough, what can you do? Make sense? Basically, think about the initially when you have your phone, what's your phone's functionality? You're actually calling somebody. Make sense? At that time, the traffic is voice traffic, right? Then later on, because the phone is getting more complicated, the phone started with the wireless network. At that time, it's a 3G third generation. And the third generation, CDMA, right? What's happening for the third generation? Besides voice traffic, we need to support the data traffic. Then at that time, the short message is getting popular, right? Because the speed, wireless bandwidth is not wide enough. Then later on, when the bandwidth, the speed is getting more and more, think about your phone. What do you do using your phone? Think about even at your own history. We used to using the phone to call somebody. Later on, we send the text. Then later, think about your phone. It's like a small computer, right?
Yes.
Right? Basically, that's the thing about all those things is related to network. And also the network's history and network's development. Okay? So what's the time?
It's 5:42.
5 minutes break. You come back for chapter 2. Okay. Has there's happy always for the day.
Yeah. This one's correct. It's 8 p.m. Link. Yeah. Right. Network. 19. D is traffic from what? Oh, shit. So funny.
home, right?
Yes.
So you're from Indonesia. Who is from Indonesia? The mom and dad.
My mom.
And my husband family used to. My husband dad used to live in Indonesia. And you are Elizabeth, right? Yes. I don't know who's quick survey. Who is taking the prelim this semester? The network prelim exam. Yeah. Raise your hand. I'm trying to ask.
Wait, it's next semester.
Oh, you're next semester. Okay. So you are taking this semester. What? Yeah. So 10, FAM, right? Yeah.
Yeah.
What else?
Oh yeah, that's a good method.
So I'm thinking, just even too many, should I, because currently we are talking about the application, then transport, then the network. I'm thinking should be halfway application, then start transport. That's what I'm thinking, but quite a few or take the exam. Because the exam typically, the exam is a kind of basic knowledge, right? So typically focus is more at the transport and the network layer.
Okay.
So application layer because it's close to what's actually happening there. And the transport and network layer is based on what actually is the foundation of the network. Makes sense? That's basically the focus for the exam. That's what I'm thinking. If too many people are taking that, should I switch the material a little bit, the order-wise? That's what I'm thinking. Anyway, let's see. I think the Ben today has a meeting. He dropped me an email. I think Ben also.
Yeah. Please.
Everybody here? We can start? So, finally, introduction is over, right? But through the introduction, I hope you guys at least have some kind of knowledge, big picture about the internet network, okay? So we will, application layer, chapter 2, chapter 3 will be transport layer, okay? So transport layer, that's an overview of application layer, that's an overview of the application. So they will talk about the few important applications, okay? Look at here, I think most of you should know those, right? First, we will talk about the principle of network applications. Then we will use the HTTP, the web, is an example, web browser as an example, talk about some of the protocols there. Then we're using SM email application, talk about the email application. Then the domain DNS service, then the P2P, then current video streaming. Okay, that's what is some kind of, just some of the application we will talk about, okay? Anyway, I know. Who watched this? I know your name. You watched this. So we'll still watch together, okay? Who else watched it? No. Totally understandable because you guys are busy doing the homework, right? And the homework one is lots of questions there, right?
Lots.
The reason is we are kind of trying to have one homework after each chapter. Makes sense? That's basic. The homework is a quick summary about that chapter. Makes sense? Okay. So that's why I understand you haven't watched this video. Okay. So that's section 2.1. So principle of application layers. I think after this one, we should have a quick, very simple quiz. Okay, let's start.
Well, welcome to the application layer. In a top-down approach, the application layer is really where it all begins. As the French would say, it's the raison d'etre, the reason for the existence of the network in the first place, the applications that the network's going to support. And we'll find that for our studies, it's also a really good place to begin. We'll start with applications that we're mostly familiar with in our everyday use of the internet. And we'll see that application level protocols like HTTP, the Hypertext Transfer Protocol, are really very human readable and very natural for us to understand. And so the application layer is a great place for us to start our study of networking. Our goal in this chapter is going to be to learn about both the conceptual and the practical implementation aspects of the network layer. We'll start by looking at the services that are provided by the underlying transport protocol right below the application layer, because anything the application layer does can only be done by using the services of the transport layer. And we'll look at two forms of interaction between the pieces of an application layer application, and that is peer-to-peer interaction and the so-called client-server model. That's been around a lot longer. And of course, we'll learn about protocols by looking at popular internet application layer protocols and infrastructure. We'll take a look at HTTP, the Hypertext Transfer Protocol, that operates between a web client and a web server. We'll also take a look very quickly at SMTP, the Simple Mail Transfer Protocol for email. We'll spend some time looking at the domain name system, the DNS, which is used to translate from names like gaia.cs.umass.edu to 32-bit IP addresses like 128.119.40.186. And we'll take a look at distributed application-level infrastructure like video streaming systems and content distribution networks. And we'll wrap up here by looking at the application programming interface, the socket API. As internet users, we're all familiar with many network applications, from social media to the web to messaging, email, multiplayer games, streaming audio and video, teleconferencing applications like Zoom, internet search, and remote login. And what's really interesting to me is that all of these applications, maybe except for email and remote login, were developed long after the internet architecture, the layers that we learned about in section 1.7, the transport layer abstractions that we'll learn about today were defined. That's pretty amazing. One might say that the internet designers got it right, since the network they invented supports applications they hadn't even dreamed of at the time. And I want to play you here a short clip from an interview with Vint Cerf, one of the fathers of the internet, as we learn in section 1.7, that notes that the internet architects maybe knew a few likely internet applications, but certainly not all of the applications that we've seen. He talks about the arrival of new applications, about layering, which we learned about in section 1.5, about the importance of abstractions, and about getting an appropriate, stable API, all of which we'll be covering here. So I think you'll enjoy this interview.
I love you, really.
Okay. I'll be in a second.
Did you imagine at the time that it would have the ramifications and implications that we're seeing today?
You know, the simple answer, of course, would be no, but it's not true. That's not a fair answer. If you think about this a little bit, first of all, remember that the ARPANET project, the predecessor, had already encountered electronic mail. A guy named Ray Tomlinson at BB&N, both Beranek and Newman, realized that he could do networked electronic mail if he just forwarded the messages through the network and got them to go to the right target machine. And then he had to figure out, okay, I get to the right machine, how do I tell it which user it is that I am supposed to be sending this message for? And he needed to separate the machine identity from the user identity, and the only character he could find on the keyboard that wasn't already in use by the operating systems was the @ sign. And so it's kind of natural, user @ host. So that's the origin of the @ sign in our email. So he does this, demonstrates it in sort of mid-1971. Everybody gets excited about this. We all realize what a powerful tool this is. It's computer-mediated communication. We no longer have to both be awake at the same time to communicate, so we can overcome time zones and everything else. And so email was already in place before internet work was even started. So that's a long way of saying that we actually had some appreciation for what this technology could do. And we used it to do a lot of the applications that we still use today: electronic mail, file transfer, remote access to time-shared machines. But of course, the most significant change after the internet finally gets operational in early '83 and then becomes commercially available in 1989 is Tim Berners-Lee's development of the World Wide Web. And to be honest, Tim releases this out of CERN in Geneva in sort of December of 1991. Nobody notices, except for a couple of guys at the National Center for Supercomputer Applications, Mark Andreessen and Eric Bina, who say, oh, this is cool. Why don't we build a graphical user interface? So they developed the Mosaic browser. They release this. It makes the internet look like a magazine with formatted text and images and eventually, audio, video, and things like that. Everybody notices. And so this introduction of this new way of sharing information on the net had a profound impact on its accessibility and utility. What we had achieved is this infrastructure that was infinitely, well, not really, but largely expandable. It dropped the barriers to access to computer communication to as close to zero as possible. We had given away the design of the internet for free with no patents or any other constraints deliberately in order to stimulate adoption and use. So as the general public encounters the World Wide Web, they have the ability to inject content into the network with very little barrier. And, of course, to get access to that information. In fact, there was such an avalanche of content that flowed in that we now couldn't find anything, and we needed search engines. So we got things like Alta Vista and Yahoo, and eventually Google, Bing, and so on. So this question of did we know what was going to happen? No. But there were milestones in the course of the evolution that signaled that this was going to be a big deal. And it was the commercialization in 1989 of the service as opposed to commercialization of the equipment like packet switches from Cisco Systems or Proteon or others. It was the commercialization of the service and the arrival of the World Wide Web that really conflated these two things. Then there's one other thing which I think was equally significant, and that's the arrival of the smartphone in 2007. This is Steve Jobs and Apple. And at that point, you see a phenomenon which is very important to understand. Two technologies that are mutually reinforcing. The mobile phone makes the internet more accessible. The internet makes the mobile phone more useful because of all the content and functionality that's on the net. And so those two things together have really colored the last decade of the evolution of the internet and on the products and services that go with it.
And then the more apps that started appearing for
Exactly right, yes, because we have a platform. So the interesting thing about all of this is the layering that's going on. The internet is a layered architecture. TCP, IP is sort of the core layer. TCP and the other real-time protocols are just above that, and then there are utility protocols like file transfer. When we get to the World Wide Web, it's another layer. The hypertext transport protocol sits on top of TCP. And then, on top of the mobile phones, we get APIs that make it easy for people to build applications even if they have no idea how the mobile telephony part works. And it's this isolation of knowledge, of necessary knowledge, and the stability of the interfaces, whether it's a stable protocol interface or a stable API, that the longevity and stability of those interfaces allow people to do things without having to know very much at all or anything about how this works underneath. So you create this opportunity for invention without a whole lot of overhead.
Well, now imagine that you want to write an application. And actually, we're going to write some networked applications in just a second. So if you want to write a networked application, what do you have to do? You've seen how complicated the internet is. Think about all those things going on under the covers from source to a destination. Well, as it turns out, it's really pretty easy to write a networked application because in a way we can abstract away all of that complexity that's happening deep inside the network. All we have to do is worry about two things. First, what are the services provided by the transport layer? And secondly, what does the API, the application layer interface, look like to these transport layer services? Now, when we want to build a network application, there are basically two styles of interaction that describe how the pieces of the network application are going to interact with each other. The first is the client-server model, and the second is the peer-to-peer model. And since the client-server model has been around the longest and was the first, let's take a look at that. In the client-server paradigm, well, there's a server and there's a client. The server is an always-on host, generally has a permanent IP address so that clients will know where to contact it, and the server may be hosted in your home, in your company, in your university, or in commercial data centers. On the client side, well, that's what we're more familiar with. Clients are going to operate by contacting and communicating with a server. Clients will typically be intermittently connected to the internet, for instance, when your phone and your laptop is connected to the internet, so they won't have a permanent IP address. And most importantly, clients do not communicate with each other. Instead, they're going to interact with servers. And the best example of a client-server protocol, well,
You guys heard about client-server architecture, right? Right? So what do you think? How about the peer-to-peer? So basically, the guy, just I'm checking. If you have the book, that guy is really famous. He's working for the Apple. He's one of the founders, created TCP because start with Apple test web. Think about the famous Einstein, lots of stuff, right? That's the guy. Basically, how everything created and still working pretty good, right? Then that's basically the only history part. Then one of the key concept in this 2.1 is two network architecture. One is client server, the other is peer-to-peer. So what do you think? Who wants to give me some kind of example of the client server applications? HTTP. So in that case, every time when you're browsing some kind of website, what's happening?
Sometimes it exists, sometimes it exists.
So basically, you're a web client. They need to have some web server somewhere, right? Right. So web server will provide service to multiple clients, client-server situation, right? How about peer-to-peer?
From computer to computer.
Computer to computer, peer. So basically, the question is, because this video is a little bit long, I want to ask you guys, we have two major network architecture, client server, right? Which most of, at least we are kind of familiar with, think about, right? Even your guys are kind of install some kind of servers. If you want to create your own website, you need to have your own web server in there, makes sense? Then peer-to-peer. The question is, for each different network architecture, what's the pro and the cons? What's the good thing about the client server? What's the good thing about peer-to-peer? Think about those when you watch this. Make sense?
detail is HTTP, where the client is the web browser and the server is the web server. In a peer-to-peer architecture, there is no server. Instead, what we have are peers in systems that are going to directly communicate with each other. They're going to request service from other peers, and they're going to provide service in return to other peers. We see that in file sharing as an example, where a peer may request files from other peers, but also serve files out to these other peers. These peers are going to be intermittently connected to the internet, and they're going to change their IP address. And so with peers coming and going, the management of these peers is going to be much more complex than in a client-server environment.
One of the great challenges in this world is
is knowing enough about a subject to think you're right.
So as we've seen, network application is going to consist of a set of interactive pieces, whether they interact in a client-server model or they interact in a peer-to-peer model. So it's not going to be a single standalone program that you program, compile, and run. Instead, it's going to be multiple programs, each of which you're going to write and compile and run. Now, when these programs are running, they're instantiated as a process. So you can think of a process as the executing version of a program. Now, so these processes are going to be communicating. If they communicate with each other inside a single computer, that's generally referred to as inter-process communication, IPC. When they're running on separate computers and when they're running on separate hosts and devices, they're going to have to communicate using messages. And that's what we're going to be interested in here. So let's see how two processes, each on different devices on different hosts, are going to communicate with each other. Well, we've talked a lot about the client-server model, and let's get even a little bit more precise with our language. When we start talking about building and programming client-server applications, we're going to refer to the process that initiates communication, that is first reaches out to the other side as the client, and the process that is contacted as the server. The application programming interface bound to the transport layer uses an abstraction known as a socket. The process is going to send and receive messages to and from sockets that it creates. And you can think of a socket as being analogous to a door. We create the door, we send messages into the door, and we receive messages back out of the door. The sending and receiving process are going to rely on the underlying infrastructure, the transport layer, network layer, and link layer, to deliver messages from a socket at the sending process to a socket at the receiving process. And it's important to note that there are going to be two sockets involved whenever a sender and receiver communicate, one on each side of that communication. Now we can dive down into some of the mechanics of actually using a socket to communicate. And the first topical...
I think many of you heard about socket programming, right? Kind of, right? Basically, when you try to create some apps to do that, typically many things are your operating system is doing for you, right? Now, basically, you can think about the socket as a gate between the application layer and the transport layer. Remember, still the similar concept is when you have a message, you need to pass it through the lower layer, and lower layer handling for you, right? Makes sense? Eventually, when you get this package on the other side, they need to distribute it to corresponding process, corresponding applications. That's basically, eventually think about your communication. Moving, before you're taking this class, mainly you're just using all kinds of application, right? Everything is basically there. When you're doing the web browsing, you never thought about actually what's happening there, right? Makes sense? That's the process you will serve for, right? That's the client server. In your most user cases, is similar to like application top to application. Makes sense? That's from surface point of view. Think about it, you are buying some stuff. Some merchant have a website, just go to the website and buy the stuff, right? Basically, it's like you're accessing that website, buying stuff. They have a server there. You just do whatever you need, right? Now, after this, so far the introduction, you know what's happening there. Application need to pass on all those handling, all those for lower layer in order to support. Make sense? Right? Now we focus. Now we learn this chapter. We focus on application layer. At the same time, like I mentioned, you need to think about what's the next layer, lower layer need to provide for this application layer. Make sense? That's the thing. Then we also mentioned we have a client server and peer-to-peer, right? Two architecture. Second thing, they want to talk about those kind of different identifiers, right? They want to see which kind of socket they are mentioning. They need to specifically target those kind of sockets, right? Like when the packet is coming through, they need to see, whether it's for your web browsing application or for your email or for your, whatever application you're doing. Make sense? So this identifier, I want to speak a little bit. This is another key concept. I want to pay a little bit attention on this part, that's why. Because this one is, this video is a little bit long, so I'm afraid you guys are lost in the middle.
Is an addressing. So think of it this way. When you want to communicate with somebody, you need some addressing information. If you're sending them a letter, you need to know the street address and the town they live in. If they live in an apartment building, you need the apartment number. If you're calling somebody, you need a phone number, maybe you need a country code, and you need a local area code. And if they're in a company, you also need to know some extension information. And it's the same thing with communicating using a socket. We need some information about how to address the messages that are going to the other end of the socket endpoint. When we create a socket, it's going to have two important pieces of information associated with it. The first is the IP address of the host, and the second is a port number. As we'll see, some port numbers are associated with a specific service and a specific protocol. For example, establishing a connection to a server on port 80 will connect you to the web server at that server. Connecting to port 25 will get you to an email server. We'll cover ports in more detail throughout this chapter. Well, way back in section 1.1, we said that a protocol defines the format, the order of messages sent and received among network entities, and actions taken on message receipt and transmission. So, to define an application layer protocol, we'll need to define the types of messages that are exchanged, their syntax, that is, what are the fields in the messages, and their semantics, what are the meanings of these fields, and what actions are taken before and after sending or receiving a message. There are two types of protocols. Open protocols, open in the sense that their message syntax and semantics and actions are all publicly available and known to all. Internet protocols, for example, are specified in publicly available RFCs, requests for comments. In our second assignment, you'll actually read an RFC. Other protocols are proprietary, meaning that they're owned by a company typically, and their operation isn't publicly known. Zoom and Skype, for example, are applications with proprietary application layer protocols. Well, now that we've got a handle on addressing and what an application layer protocol might look like, let's turn our attention downward, if you will, and let's look at the transport layer, and in particular, ask ourselves the question, what are the kinds of services that might be provided by the transport layer to the application itself?
Stop asking research questions to ChatGPT. Its answers are not reliable, and they are...
Reliable data transfer is a service that's needed by a lot of applications. For example, file transfer or web transactions. That is, we need to be able to transfer data reliably from one process to another. But not all applications need reliable data transfer. Packet audio, for example, voice and video, can actually tolerate some packet loss. Some applications may need timing guarantees. Telephony and interactive games really require low delay to be effective. So a transport layer might provide a delay guarantee from sending process to receiving process. Other applications require a certain amount of throughput in order to be effective. For example, streaming video needs a certain amount of throughput in order to send the number of bits per second required by the video. Other applications, which we'll call elastic applications, are able to make use of whatever throughput they can get. And finally, a transport layer might provide security services, for example, encryption on transmitted data. And here are the transport service requirements of some common internet applications. You can see the first three: file transfer, email, and web documents cannot tolerate data loss, and they're generally elastic. They can make do with whatever throughput they can get, and they're generally not real-time, time-sensitive applications. On the other hand, real-time audio and video, streaming audio and video, and interactive games do tend to be a little bit loss-tolerant, but have much stricter throughput and timing requirements. The Internet's transport layer only offers two types of services: TCP service and UDP service. TCP provides reliable data transfer between a sending and a receiving process. Also, the sender is flow controlled, so it won't overflow the amount of available buffers at a receiver. The TCP sender is also congestion controlled, and TCP is connection oriented, meaning that handshaking is required between the client and the server before data actually begins to flow. And finally, TCP does not provide any timing guarantees, nor does it provide throughput guarantees or security services. Well, the second type of transport service provided by the transport layer provides actually even less than TCP. UDP service provides unreliable data transfer. That is, there are no guarantees made. UDP will make a best effort attempt to deliver data from sender to receiver, but makes no promises about reliability. It also doesn't provide flow control, congestion control, timing, throughput, or security guarantees. So you might ask yourself, why is there a UDP in the first place? And the answer to this question that we'll see is adopted by a number of application layer protocols is that we can build these additional services that are not provided by UDP on top of UDP in the application layer. And here you see the underlying transport services used by popular internet application layer protocols. I think it's fair to say that TCP is by far the most widely used transport service, although, again, as we'll see, there are good uses for UDP as well. Well, let's wrap up our discussion of application layer principles and practice just with a quick note on security. The initial socket abstraction developed in the 1980s had no notions of security associated with it. There was no encryption of data that was sent into sockets. There was no notion of endpoint authentication, proving to the other side that you are who you say you are. If you wanted to do that, you actually had to build it up in the application layer itself. We'll see later that there's a widely used security layer. Actually, it's more like a shim layer known as Transport Layer Security, TLS. It's implemented in user application space on top of TCP sockets and provides encryption, data integrity, and endpoint authentication services that can be used by an application. Well, that wraps up our quick introduction to the principles and practices in the application layer. We saw that an application is actually a distributed set of interacting processes that exchange messages. We learned about the client server and the peer-to-peer paradigms for structuring applications. We talked about sockets, which we saw as the principal internet abstraction for communicating among processes. We're going to learn a lot more about sockets. We talked about addressing. Then we talked generally about transport layer services. What are the services that a transport layer might provide up to an application? And we wrapped up with a quick discussion of security. Coming up next, we're going to start looking at specific applications and their application layer protocols. We're going to start with the web and the hypertext transfer protocol, HTTP.
For this section, to bring out some of the key concepts. Some already asked you guys, right? Like the difference between the client server and the peer-to-peer, right? Pro and the cons. And then talk about when we try to have the socket, the identifier, how to specify different socket in different situations. Make sense? This one is a very quick, only 4 questions. server paradigm. First one, you pick which of the characteristics below associated with client server approach?
D.
B. HTTP using the client server, right? What else?
C.
So for client server, for the server need to be what? Always on. What else?
E.
I heard D as in dog. Everybody pick the D? We pick the D. I also heard E as in egg.
Yes.
So both of So for this one, okay. Client server later. For this one is BCE. Okay, later on we'll review. Okay. So basically for the server, they need to have a what? Typically because they need to have a permanent IP address, right? Okay.
Yep.
And then coming back when this is first one, then coming back for the peer-to-peer. What do you guys pick?